with our session 2 of group 13 elements, right? So we were doing the physical properties and the chemical properties. We have already discussed the physical properties, and now the remaining chemical properties we need to discuss in today's class, and some compounds of boron we will discuss in today's class also, right? So students are requested to drop down their names for attendance purpose. We will be starting in a while. Okay, so we'll start now. See, hydrolysis of compounds. What do you mean by hydrolysis? Basically, when you add water to a compound, the chemical reaction that it undergoes is known as what? Hydrolysis, right? So in trivalent state, what do you mean by trivalent state here? See, for example, let us say we are having BCl3, we are having BaCl3. So these elements, boron, aluminium, that is the central element, is present in its trivalent state, right? That means the oxidation state here of the central atom, not central metal atom, because boron is a non-metal obviously, right? So central atom exists in +3 oxidation state here. That is why we are saying here that in trivalent state, most of the compounds being covalent, because they are forming covalent compounds, they are hydrolyzed by water, right? Now, what are the product of hydrolysis? The product of hydrolysis is tetrahedral species, right, of the formula MOH4 negative. Now, what is M here? M is the central atom. For example, let us say that BCl3 we are taking, right? On reaction with water, on hydrolysis with water, it will form what? BOH4 negative. Now here you can also relate to the hybridization. BCl3, if you see, it is trigonal planar in nature, right? So it is of sp2 hybridization. While here, if you will see, this is a tetrahedral species. So what is the hybridization of the tetrahedral species? That is sp3 in hybridization. That means on hydrolysis, the trivalent state compounds, right, changes into sp3 hybridization. That means the hybridization is changing from sp2 to sp3 on hydrolysis, right? Aluminium chloride, however, it forms a different compound. It forms octahedral ion. Here you can see, because 6 water molecules are there, so the coordination number is coming out to be 6, or you can say that the side atoms are 6, right? So occupancy of 6 positions are there, and we know that the hybridization for octahedral is what? sp3d2, right? So if you will hydrolyze AlCl3 with water in presence of some acid, right? Let us say we are taking acid H plus I am resembling here. It can be any acid. The H plus can come from any acid. It will form what? AlH2O6 and then 3 plus. It is forming a cation of octahedral nature, and we know that the hybridization for octahedral geometry is what? sp3d2, right? Now coming on to the complex formation, because here you can see that they are smaller in size, boron, aluminium, right? These elements are smaller in size. That is why they have greater tendency to form complexes than that of the S block elements. So now if you will compare the size of S block elements and let us say group 13 elements, here let us say we are saying group 1 here, then group 2 here, then we are having group 13 here. We know that across the period size decreases. That means what? That the group 13 elements of the similar period, if you will compare the elements of group 1, group 2 and group 13 which belong to the same period. For example, let us say second period we are having, right? So it will be lithium, hydrogen, helium, lithium, beryllium and then boron, right? These three belongs to the second period. So obviously if you will compare the size, we know that size decreases across the period. So boron will have a smaller size than that of lithium and beryllium. And due to their small size, the group 13 elements have a strong ability to form complexes when they are compared to S block elements, right? Here you can see that boron is forming a complex here, right? Aluminium is forming a complex here. So why they are forming complexes? Because of their small size and greater charge. Now how come greater charge can be explained? If you will take group 1, the oxidation state comes out to be +1. Right? Group 2 has a common oxidation state of +2. But here if you will take group 13, they have a common oxidation state of +3. Right? So charge is also greater. So the interaction between these oxygen, you can say, because oxygen is binding here with aluminium, or nitrogen and oxygen is more. Why? Because the charge on the central atom, aluminium or boron, is more. While if you will compare to S block elements, they have a charge of only +1 and +2, right? So the elements which have small size and greater charge have more complex forming ability, right? So because group 13 elements have greater charge and small size, that is why they have more ability to form complex than that of the S block elements. Now coming on to reactivity towards air. So boron, if you take it in crystal form, it is unreactive, right? It will not react with air, right? While if you will take amorphous boron, see, solids have two different type of structure that you will learn in 12th class also: crystalline solids and amorphous solids. In previous session, I guess I have explained this in detail, right? So amorphous boron, if you will make it react with air, it will form what? B2O3. It will form B2O3. While aluminium, as we have already studied, what happens here is that on reaction with little amount of air, that means little amount of oxygen, it forms a protective layer around it, right, which is of Al2O3, right? Let us say, for example, we are having aluminium rod here, right? I make it react with oxygen. What happens here is that with some part of oxygen, it forms a coating of Al2O3. Now Al2O3 is a very hard substance. If you take it, has a very high melting point, right? So now further aluminium will not react with oxygen. Once it has formed a coating of Al2O3, it will be passive to reaction by making reaction with oxygen itself, right? So here you can remember this one, that aluminium forms a oxide layer on its surface which protects the metal from the further attack, and this is the reason why we use aluminium pans at our home for cooking, right? Now amorphous boron and aluminium, when they react with air, the respective compounds that are formed are B2O3 and Al2O3, and with high temperature, and with dinitrogen, they form what? Nitrides. Right? So here you can remember E as group 13 element. It reacts with oxygen to form oxide of the formula E2O3. For example, B2O3, Al2O3 and so on. And group 13 elements react with nitrogen directly at high temperatures to form nitride of the type En. Right? So boron nitride will be Bn, aluminium nitride will be Aln, right? And so on. Now this is very important, that boron nitride has graphite-like structure. That is why it is also known as inorganic graphite. Inorganic graphite. The details of graphite structure, we will do it in basically next group 14 elements. When we will study, we will do the whole structure of graphite with elaboration there. Right? So meanwhile, you can remember that graphite has a layered structure and it is made up of carbon atoms. Here you can see that carbon is in its trivalent state. Here you can see that sheet-like, layer-like structure is formed. This is one sheet, then this is second sheet, then this is third sheet, and between these sheets there is pi electrons. what happens here is, see, in graphite structure, carbon is bonded to 3 other carbons, and 1 electron that is left here, it basically forms a sea of electrons here, right? So each carbon atom will have one electron free, and this is the reason that why graphite conducts electricity. It conducts electricity due to this 4th electron which is present on each carbon atom, and this is known as what? Pi stacking. This is known as pi stacking of graphite. So graphite has a layered structure. Similar to that only, boron nitride also has the same structure. Here you can see, but instead of carbon we are having what? Boron and nitrogen. Layered structure you can see. Now this is important, this thing is very important. If you will compare the gap between the layers, here you can see 0.67 nanometer, here you can see 0.66 nanometer. This means that the spacing between layers is less for boron nitride as compared to that of graphite, right? So 3 things you have to remember. First, you have to remember that boron nitride, how can it be prepared? By reacting boron with nitrogen at higher temperature, at elevated temperature, right? Second thing that you need to remember is that boron nitride has a graphite-like structure. It has a layered structure similar to that of the graphite. Third thing that you need to remember here is that boron nitride is also known as what? Inorganic graphite. Right? And the fourth point that you need to remember here is that the distance between the sheets or the distance between the layers is less for boron nitride when you compare its structure, or when you compare the distance of layers for boron nitride and graphite. So here the distance will be less and here the distance is greater. Okay. Now coming on to reactivity towards air again. So nature of the oxides that are formed. See, boron is what? A non-metal, right? Aluminium is what? A metal. And some of its properties of aluminium basically resemble to boron also. Then you have what? Gallium, indium, thallium, which are purely metals, right? We already know that non-metallic oxides, if you will see, they are acidic in nature. Non-metallic oxides are acidic in nature, and metallic oxides are what? Basic in nature. Metallic oxides are basic in nature, right? So here if you will compare B2O3, which is an oxide of a non-metal, it is acidic in nature. Aluminium and gallium oxides are amphoteric in nature. Amphoteric means they can behave as acid also, and they can. And indium and thallium, they have basic properties, right? So they are basic in nature. Now reactivity towards acids and alkalis. So boron does not react, it do not react with acid and it do not react with base also, even at moderate temperature. However, if you will see aluminium, it dissolves with dilute HCl to liberate hydrogen gas, right? To liberate hydrogen gas. That means it has the ability of converting H plus into hydrogen, and aluminium itself gets oxidized to aluminium 3 plus. Yeah. Now next, if you will take concentrated nitric acid, that is HNO3. If you will treat aluminium with concentrated nitric acid, it forms a protective layer oxide, that is of oxide on the surface, right? So it does not react with nitric acid. Why? Because already we have studied that with a minute amount of oxygen, it forms a layer of Al2O3, which prevents further attack of aluminium from oxygen also, and from acids like concentrated nitric acid also, right? Now aluminium reacts with aqueous alkali to liberate dihydrogen. Again you can see here that it reacts with dilute HCl also to give hydrogen gas, and it reacts with aqueous alkali like NaOH oxygen gas. And what is the byproduct here? Sodium tetrahydroxoaluminate, right? Or you can just remember it as aluminate ion, AlOH4 negative. So this is known as what? Aluminate ion. Now reactivity with halogens to form trihalides. Now this is very much important, that thallium I3 is not formed. Thallium I3 is not formed. Why it is not formed? Because thallium wants to exist in its +1 oxidation state, because +1 oxidation state of thallium is more stable than that of +3 oxidation state due to the inert pair effect that we have covered in the last class. Right? What was the inert pair effect? That down again aluminium also you can prepare this way, aluminium chloride, that Al2O3 you take, reduce it with carbon, because carbon has the greater affinity for oxygen. So carbon will gain oxygen, CO, and the aluminium which is left will combine with Cl2 to give you what? Aluminium chloride. Now, because thallium Cl3 is basically not formed, what happens here is that thallium Cl3 breakdowns into what? Thallium Cl plus Cl2. Plus Cl2. Here thallium is in +3 oxidation state, here thallium is in +1 oxidation state. So obviously the forward reaction is more favorable. Why? Because thallium +1 is more stable than that of thallium +3 due to the inert pair effect. Now this is a question here, that white fumes appear around the bottle of anhydrous aluminium chloride. So if you will take anhydrous aluminium chloride, why? This you can see that the white fumes are appearing, right? So what happens here is, with atmospheric moisture, means what? That AlCl3 on reaction with water, it liberates HCl gas. It liberates HCl gas, and these fumes are due to the HCl gas, and this water is basically the moisture from atmosphere, right? So these moist HCl, they appear white in color. That is why we are having fuming white fumes around the bottle of anhydrous aluminium chloride. Now this you tell me, which one of the following compounds has similar structure to that of graphite? Okay. Yes, option 1 is correct. So Sarayu, you are correct with your answer, that boron nitride has a similar structure to that of graphite. Good. Now coming on to reaction with water. So both boron and aluminium, they do not react directly with water. However, amalgamated aluminium reacts with water evolving hydrogen, right? What is amalgam? Basically, when you have alloy of metal and mercury, right? Alloy of metal and mercury is known as what? Amalgam. So sodium plus mercury alloy will be called as sodium amalgam. Aluminium mercury alloy will give you what? Aluminium amalgam, right? So amalgam of aluminium reacts with water to give you what? AlOH3, rendering hydrogen gas, right? While if you will take gallium and indium, They do not react with pure cold water also and hot water also. But if you will take thallium, thallium forms oxide layer on the surface, same as that of aluminium, right? So only thing that you need to remember here is that boron, aluminium, gallium, indium, they do not react with water. Thallium forms an oxide layer on the surface, right? And the second exception is that amalgam of aluminium reacts with water to give you what? Hydrogen gas. Now reaction with carbon. So non-metals or metals on reaction with carbon, they basically yield what carbides, right? Carbide is what? Carbon having a negative charge. Carbon having a negative charge will give you what? Carbides, right? So here you can see that boron plus carbon will give you what? Boron carbide. Aluminium plus carbon will give you what? Aluminium carbide, right? Now this is very important, that aluminium carbide, this is ionic in nature and forms methane with water. So if you react Al4C3 plus water, that will give you what? Methane, right? That is why, because the product here is obtained as methane, it is known as what? A methane. Actions of this compound, we will discuss them in the next class itself, right? So boron forms a number of hydrides, and these hydrides collectively are known as what? Boranes. One of them is what? B2H6, which is specially called as diborane, right? So BH3, if you will form the dimer, it will form what? B2H6. Double the amount, boron 2, hydrogen 3 into 2, that will give you 6. That is why its name has been given as diborane. So boranes are stable. But if you will take the hydrides of aluminium, gallium, indium, thallium, their stability decreases down the group. Here if you will see aluminium hydrogen, gallium hydrogen, then indium hydrogen, then thallium hydrogen, what? Down the group. Obviously, is it fine? Because if you will compare, okay. So we were discussing about the anomalous properties of boron, right? So the reasons why it is having anomalous properties is small size, high ionization energy, highest electronegativity, and the absence of the vacant d orbital, right? This much we have discussed. Now see, anomalous nature of boron is what? How it is differing in properties with rest of the elements. So it is a non-metal, while if you will see the other members, they are metallic in nature. First point of difference. Second point of difference is that boron shows allotropy, while other members do not show allotropy. As we have already studied that isotopes of boron also we have studied, that B10 and B11 are available, right? So boron has allotropes, but rest of the members are not having allotropes. Now it has the highest melting point and boiling point in group 13. It only forms covalent bonds, right? It only makes covalent compounds, while the rest of the members have the ability to form both of the compounds. That means they can form ionic compounds also and covalent compounds also, depending upon the electronegativity difference of the central atom and the side atom, right? Now next is that halides of boron exist as monomers. For example, BCl3, BF3, they all are what? Monomers. While AlCl3 exists as a dimer. As we have already studied its bridge structure, that 2 chlorines were in bridging position and the rest of the 4 chlorines were at terminal positions, right? So AlCl3 exists as Al2Cl6, that means as a dimer. While the halides of boron, if you will see, they exist as monomers only. Now oxides and hydroxides of boron are weakly acidic, while aluminium, if you will compare, they are amphoteric, and rest of the elements, if you will compare the oxides, they are basic in nature. This also we have already explained, that increase in metallic character is there from from up to down, basically down the group. If you will compare, that increase in the metallic character is there. So what happens, that we know that metallic oxides are basic in nature, right? So the basicity of oxides also increases down the group. Now, boron can be oxidized by nitric acid to give what? Boric acid plus nitrogen dioxide. But if we will compare aluminium, as we have already studied, that due to the formation of the oxide layer on its surface, aluminium does not react with concentrated HNO3. Now coming on to the diagonal relationship. So what is the basis of diagonal relationship? Already we have studied in group 1 and group 2, right? What is diagonal relationship? That similar properties is there of the elements which are present diagonal to each other, right? For example, let us say we are having what? Lithium, beryllium, then boron, carbon, nitrogen, oxygen, fluorine, neon. Then here we are having what? Sodium, potassium, either magnesium, sodium, magnesium, aluminium, silicon, right? So lithium and magnesium were having diagonal relationship, beryllium and aluminium are having diagonal relationship, and boron and silicon are having diagonal relationship, and these diagonal relationships are due to their similar sizes. Due to their similar size, what happens is that they show some properties which are similar to each other, some chemical properties or physical properties they exhibit similar to each other. So let us see what are the properties which are common to boron and silicon. First, both of them are non-metals. Both of them are semiconductor in nature. Boron and silicon, they form covalent hydrides. So hydride of boron we have already studied, they are known as what? Boranes. Similarly, hydrides of silicon are known as what? Silanes, right? That we will deal in group 14 itself. Both form covalent and volatile halides, right? For example, BCl3 is a covalent halide, silicon Cl4 is also a covalent halide, and they both are volatile halides, right? So they react with water which is present in air, or you can say moist air they react with and form what? This forms orthoboric acid, that is H3BO3 plus HCl gases is evolved. Similarly, here also SiOH4 is formed and HCl gases evolved. This reaction you can remember a bit like this. For example, let us say boron and chlorine we are having, and what we are having? H plus and OH minus, right? We know that chlorine is highly electronegative in nature and it is more electronegative than that of boron. So let us give it a negative charge and let us give this boron a positive charge. Now what happens is that positive combines with negative, and here also positive combines with negative. So product will be what? BOH3 plus HCl. Similarly, here also, because chlorine is more electronegative than silicon, give it a negative charge, give silicon a positive charge, give hydrogen a positive charge, and give OH minus a negative charge, and then combine positive with negative. That means combine silicon and OH and combine H and Cl. So it will give you what? SiOH4 plus HCl. This is a general trick to remember these equations. Okay. Now, they both form solid oxides, right, which gets dissolved in alkalis forming borates and silicate. So if you will take boron oxide, right, it will dissolve in NaOH to give you what? Borates. Similarly, if you will take silicon oxide, it will react with alkali to give you what? Silicates. Now, they both are electropositive metals. They both react with electropositive metals and give binary compounds which yield mixture of boranes and silanes on hydrolysis. Now this is important. This we will study when we will study the compounds of boron. This you will get more information about when we will study compounds of boron. Next, now you need to answer these questions. Which of the following statement is correct? Boron and aluminium halides behave as Lewis acid. Aluminium forms AlF6 3- but boron does not form this. P-pi back bonding occurs in the halides of boron and not in those of aluminium. And fourth option says all of these. Anyone with the answer? BCl3, AlCl3, let us say for example, are Lewis acids or not? First point is this. Second says that aluminium can form AlF6 minus, but boron cannot form BF6 minus. Third option says that p-pi back bonding, that the case of back bonding that we studied in halides of boron is applicable to boron only and not in case of aluminium. And fourth says that all of these are correct. What should be the answer according to you? Anyone with the answer? See, we already know that trihalides, if you will see, BCl3, AlCl3, they are electron deficient in nature. Why? Because only 3 bonds are being formed. 3 bonds means what? That 6 electrons are there. That means the octet is not complete. So, both of them are behaving as what? Lewis acids. Second one is obviously true because boron is not having vacant d orbital, right? So it can form maximum of 4 bonds, but here it is forming what? 6 bond. So this compound is not possible because vacant d orbital is not there for boron, and that is why it cannot expand its octet. It cannot make it cannot make more than 4 bonds, right? Because it cannot accommodate more than 8 electrons. 4 bonds means what? 8 electrons. While aluminium has vacant 3d orbital, so it has the ability to expand its octet and therefore it can form 6 bonds here. Now p-pi back bonding, if you will see that it does not happen in case of aluminium, it only happens in case of boron. For example, we have studied that BF3 we are having what? 2p bonding, right? p-pi back bonding, due to which the electron deficiency of BF3 molecule is lowered. And fourth option is all of these. So all of these options are correct. Now next come on to compounds of boron. First one is borax, sodium tetraborate decahydrate. Now this is very important. It can be represented by 2 formulas. Borax can be represented by 2 formulas. Either you represent it as Na2B4O7.10H2O, or you can represent it by this formula B4O5OH4 whole negative. This is the correct way of representing borax, right? So you can use the either of the formula, however, but this is the correct way of representing, as you can learn the structure of borax through this formula. See what you need to, right? Now you are 4 borons with 4 OH. So this is the main structure of borax which you need to learn. It is very important from the examination point of view. Right? Now borax on dissolving in water, it gives what? Orthoboric acid, which is another important compound that we need to learn for boron. Again, I am repeating that boron compounds are very much important from the examination point of view, right? Their structures, their properties, their preparation. Basically, this is the area for FAQs, that means frequently asked questions. Now, next you come on heating with ethyl alcohol and concentrated H2SO4, it gives what? Triethyl borate. It gives what? Triethyl borate. So, borax on treatment with H2SO4, it will give you what? Boric acid, which is H3BO3. These reactions are important. Now, this H3BO3 reacts with what? It reacts with ethyl alcohol, or you can also say it as ethanol, to give you what? Triethyl borate, right? So BOC2H53 is known as what? Triethyl borate. Now this burns with a green flame. This burns with a green flame. Now you can get a question like this, that compound A reacts with H2SO4 to give you boric acid H3BO3, which on further reaction with ethyl alcohol gives you compound B, which burns with a green flame. Tell me what is A and B. So A will be what? Borax, and B will be what? Triethyl borate. right? So this way you can get the questions. Now on heating, first borax loses water. Here you can see that 10 water molecules have been evaporated. So here it becomes what? Na2B4O7, which on further heating will give you glassy bead. Glassy bead is a mixture of what? Sodium metaborate, right? BO2 minus is known as what? Metaborate, and when you combine it with sodium, it will give you what? Sodium metaborate plus boric oxide. This combine to give what? Glassy bead. Now this borax bead is used for detection of colored basic radicals under the name borax bead test, which is again very important from your examination point of view. Right? For example, let us say we are having what? We want to detect that in your salt or in your compound there is cobalt present or not. That we can detect from boron itself, right? How we can detect that? Let us say you are having what? Cobalt sulfate. You heat it, it will give you what? Cobalt oxide plus SO3 gas, right? Now this cobalt oxide will react with what? B2O3. Now, how B2O3 was formed? Here, boric oxide was formed when you heat what? Borax. First, it loses water, and then again if you heat that, you will get what? Boric oxide. This boric oxide combines with metal oxide to give you colored compounds which are known as what? Metaborate. So, cobalt metaborate is blue in color. So, if you will get blue color, that means what? That your compound contains cobalt in it. Right? Similarly, iron gives iron metaborate, which is green in color. Chromium gives green color. Nickel gives brown color. So these are characteristics color of different metal ions which can be detected through borax bead test. Again, I am repeating, for borax bead test, you need to react what? B2O3 plus metal oxide, that will give you what? Metal metaborate. Right? So metal metaborate are of different colors for different metals, and that is how you can identify that in your given compound a particular metal is present or not. Again, the colors are important. Cobalt, the color is blue. Iron, the color is green. Chromium, the color is green, and nickel, the color is brown. So here you can see the bead test for chromium, that is greenish in color. So this is due to the formation of what? Chromium metaborate, which is green in color. Now come on to orthoboric acid. So orthoboric acid, you need to remember that it has a layer like structure. First you draw a hexagon, right? This is a trick for drawing H3BO3. First you draw a hexagon, then you draw 2 oxygen here, 2 hydrogens here, right? Then again 2 oxygen here. I'll once again make it, make it a bigger one. So boron and boron here, oxygen, 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 and then hydrogens here, right? And these oxygens are also connected to what? Hydrogens again. So this is a typical unit of what? H3BO3, right? So it has a planar structure, right? Its structure is formed in the form of a layer, same as that of the graphite as we have studied, right? With BO3 units joined by hydrogen bond. So here you can see this is a BO3 unit. This is a BO3 unit. Sorry, this is a BO3 unit. They are together joined by what? Hydrogen bonds. Again, I'll show you. This is a BO3 unit. This is a BO3 unit, and they both are joined by what? Hydrogen bonds. Now orthoboric acid, it is basically of soapy touch and it is a white crystalline solid. It is highly soluble in hot water, however it does not solubilize completely in cold water, right? How can it be prepared? Now this is very important, that when you heat borax with HCl and water, it will give you what? NaCl plus boric acid. Now boric acid can be represented as H3BO3 also, and it can be represented as what? BOH3 also. Now in spite of having OH, it is an acid. in spite of being OH, it is an acid. So let us explain that how boric acid has a acidic behavior in spite of having 3 OH groups in its formula. Okay. So here you can see that what happens here is that BOH3, see, someone which gives H plus is known as what? Acid. And someone which accepts H plus is known as what? Base, right? So to be acidic in nature, one must release H plus ions. Here what happens is that boric acid on reaction with water, you are having H plus and OH minus ions in water. What happens is that this BOH3, because this is having 6 electrons. Here you can see that boron is completing only its sextet, right? It is not completing its octet. So it is electron deficient in nature. Now what happens, because it is electron deficient in nature, it accepts OH minus and forms what? BOH4 negative, right? And you are left with what? H plus here. So indirectly it is giving H plus in the solution by accepting OH minus. That is why orthoboric acid is acidic in nature, right? Its way of behaving an acid is different from other acids. Other acid give H plus ion in the solution. Now here what happens, that it accepts OH minus, right? And indirectly it gives what? H plus ions in the solution. That is why it is acidic in nature. Now one BOH3 releases one H plus and therefore it is a monobasic acid. It is a monobasic acid. When you heat H3BO3, it will give you what? Metaboric acid, which is of the formula HbO2. And again you heat this metaboric acid, that will give you what? Boric oxide, or it is also known as boric anhydride. It is also known as what? Boric anhydride. Okay. Now one of the preparation of boric acid is this, that you heat, that you treat borax with HCl and water, you will give what? You will get what? Boric acid, right? Now it is also formed by the hydrolysis of most boron compounds. For example, let us say that you are having what? Boron hydrides you will have, for example, diboron we are having, or BCl3 if you take, or BF3 if you take, right? When you hydrolyze some compounds of boron, such as its hydrides or halides, you will get what? BOH3, that is orthoboric acid. Okay. Now from borazine we will continue in the next class, I think. From borazine we will continue in the next class. Some more compounds we need to discuss, right? Borazine is there, boric anhydride is there, right? And some compounds of aluminium also we will discuss in the next class, and then we will complete the group 13 in the next class itself, right? So that's all for today. Happy learning to all.